10 million people reside within the borders of Tajikistan, a landlocked nation in Central Asia characterized by its limited fossil fuel reserves and economic constraints. Why would a country of this scale attempt to construct the tallest dam ever conceived by human engineering? It seems like an impossible ambition for such a small population. Yet the answer lies in the strategic necessity of energy independence and the unique geography of the Vakhsh River Valley. 335 meters is the planned height of the Rogun Dam, a structural feat that will surpass every existing dam and the majority of the world's most famous skyscrapers. One can notice how the massive earth-filled structure gradually rises within the narrow, remote mountain corridor. Engineers have calculated the total cost of this monumental undertaking at approximately $8 billion. The process is only gaining momentum as the project nears its next critical milestones. It only looks obvious that a dam provides power, but in reality, the scale here is equivalent to the combined output of several modern nuclear power units. 3,600 megawatts of electricity will be generated once the turbines reach full capacity. The camera glides along the massive construction site where hydraulic equipment maneuvers with steady precision. This output will transform the region's entire energy landscape. But this is just the beginning of the story. The investment represents a significant portion of the national wealth, effectively staking the future of the entire country on a single infrastructure point. To comprehend the motivations behind such a massive industrial risk, one must examine the historical circumstances and the technical evolution of the region's water management. Everything only gets more complicated as the timeline moves further back into the past. The Vakhsh River flows with immense force through the valley, providing the raw kinetic energy required for such a project. This transformation of natural flow into high-voltage electricity follows a sequence of complex mechanical stages. The journey of this ambition began decades ago, rooted in a different era of industrial planning. From here, the narrative shifts toward the origins of the project to explain its current scale. 1960 was the decade when the conceptual foundation for the Rogun Dam first emerged, long before the technological advancements of the 21st century. Why would engineers attempt to obstruct such a violent mountain torrent in a remote region? One might assume the project was a modern ambition, but it was actually a strategic product of the Soviet Union's industrialization drive during the height of the Cold War. Moscow prioritized the transformation of its peripheral territories, specifically targeting Central Asia for massive infrastructure development. The Vakhsh River became the primary focus of these plans due to its status as a critical tributary within the Amu Darya system. It is visible how the river gains immense kinetic energy as it descends through high mountain terrain characterized by dramatic elevation drops. This geography created a rare environment, one of the few places on Earth physically capable of supporting ultra-high dam structures. But this is just the beginning. 1976 marked the official launch of the Rogun project by the Soviet administration. The objective was defined with absolute technical clarity: to construct a barrier that would surpass every existing hydropower facility in the world. This structure was designed to exert total control over the river's flow, generating electricity on an unprecedented scale, while simultaneously regulating water distribution for the entire surrounding region. At first glance, the plan seemed unstoppable, but in reality, geopolitical shifts intervened. Everything only gets more complicated as the timeline reaches 1991. The collapse of the Soviet Union triggered a period of extreme instability, leading Tajikistan into a devastating civil war that caused the national economy to undergo a complete breakdown. One can notice the slow deterioration of the construction site during this era, as the partially completed structures were left entirely abandoned to the elements. The massive concrete and earthworks sat silent for more than 2 decades, waiting for a change in the political and financial climate. The process is only gaining momentum again after this prolonged period of stagnation. It would take more than 20 years of silence before the Rogun project was granted a genuine opportunity for revival and reconstruction. The transition to the next level of development required a complete reassessment of the existing ruins. Thus, the abandoned site began its slow transformation back into a centerpiece of regional engineering. 1,099 feet is the exact height the Rogun Dam will reach upon its completion. This dimension, equivalent to approximately 340 meters, establishes the structure as the tallest dam ever constructed on the planet. Why is such a massive vertical scale necessary for this specific project? Engineering requirements dictate this height to manage the immense hydraulic pressure of the Vakhsh River while maximizing the gravitational potential for electricity. One can notice how the sheer scale of the construction site dwarfs the heavy machinery operating at its base. The Rogun hydropower plant integrates 6 individual turbine units into its design. These components generate a total installed capacity of 3,600 megawatts. At first glance, this figure represents mere technical data, but in reality, it carries enough energy to double the entire current electricity output of Tajikistan. This creates a significant surplus of power during the summer months when the glacial melt is at its peak. The process is only gaining momentum. It is visible how the dam body takes shape without the use of conventional solid concrete. Instead, engineers utilize a rock-fill design featuring a central clay core. The structure consists of hundreds of millions of tons of rock and gravel, which are compacted layer by layer with high tonnage rollers. Everything only gets more complicated as the elevation increases. The clay core functions as a flexible and impermeable barrier against water seepage. Meanwhile, the massive rock-filled shoulders on either side provide essential structural stability and energy absorption for the entire massif. 13 cubic kilometers of water will eventually fill the reservoir located behind this barrier. This capacity defines Rogun as one of the largest reservoirs in the entire region. Such a vast volume allows for the precise regulation of seasonal flow across different climate cycles. It ensures more stable power generation during periods of low rainfall and provides critical support for irrigation in downstream agricultural areas. One can notice the water level rising gradually against the reinforced slopes as the dam reaches its final height. The material lays in an even layer across the construction site, ensuring the project moves toward its final operational state without haste. 4 massive diversion tunnels through the mountain range serve as the starting point for this monumental engineering task. Why is it impossible to begin the construction of the dam directly within the existing riverbed? It only looks obvious that a dam can be built in moving water, but in reality, the entire foundation area must be kept completely dry to ensure structural integrity. At first glance, the task of rerouting a natural water source seems simple, but this requires redirecting the entire flow of the Vakhsh River away from its ancient path. Diverting the river is the mandatory first step. Engineers drill through the solid rock of the mountainside to create 4 distinct passages. Each of these tunnels extends for a distance of more than 1 kilometer in length, carving a subterranean path through the earth. One can notice how the diameters of these passages reach tens of meters, allowing them to handle the immense volume of the diverted water. But this is just the beginning. The history of the project is visible in the construction of the tunnels themselves. 2 of these structures were originally carved out during the Soviet era, later requiring extensive rehabilitation and reinforcement to meet modern safety standards. The remaining 2 tunnels were excavated and finished during the active restart phase of the project. The process is only gaining momentum. Massive boring machines and explosive charges work in tandem to hollow out the mountain. The camera glides along the smooth, reinforced concrete walls that must withstand the constant pressure of the rushing Vakhsh River. These tunnels ensure that the water bypasses the construction site entirely, leaving the riverbed empty for the builders. Everything only gets more complicated as the main construction phase finally begins. The river now follows its new artificial path, flowing through the heart of the mountain. This clearance allows for the placement of the dam's foundation on the dry rock of the valley floor. The water moves through the 4 reinforced passages, leaving the primary site ready for the next stage of the industrial process. Tens of meters of weathered soil and loose rock had to be removed from the valley floor before the Rogun Dam could begin to take shape. Why was such a massive excavation necessary when the valley floor already appeared solid? It seems simple to build upon the natural ground, but in reality, any weak material would compromise the integrity of the entire structure. The removal of these upper layers continued until engineers reached the stable, unweathered bedrock. This foundation treatment is only the beginning. Specialized drilling rigs penetrate the rock mass to reach natural fractures located deep beneath the surface. One can notice how high-pressure grout is injected into these boreholes to seal every microscopic void. This process significantly reduces potential seepage, increases the cohesion of the rock, and establishes a barrier to control groundwater flow. In parallel, a foundation drainage system is integrated into the bedrock. This system serves a single technical purpose: to reduce uplift pressure beneath the dam for its entire service life, which spans decades. The process is only gaining momentum. Rock slopes surrounding the site require their own stabilization sequence before the main embankment can start. Engineers utilize rock bolting and the installation of heavy steel mesh to prevent any shifting of the stone mass. Shotcrete is then sprayed across the reinforced surface, while drainage channels are carved out to ensure long-term stability. The equipment gradually moves across the vertical faces, securing the valley walls against the forces of nature. One can notice how the dam body rises in strictly controlled stages once the foundation and slopes meet every safety requirement. Sand and gravel are either extracted directly on the construction site or transported from nearby zones by heavy machinery. These materials are placed in thin, precise layers that do not exceed a few dozen centimeters in thickness. Large compactors then pass over the surface ceaselessly to ensure the material reaches the required density. This layering technique is designed to minimize uneven settlement and provide the structure with permanent stability. At the center of this massive embankment, a clay core is constructed simultaneously with the outer shells. Everything only gets more complicated. The clay core must be carefully protected throughout the build to maintain its impermeability against the weight of the reservoir. Engineers monitor settlement, internal water pressure, and the overall deformation of the dam using high-precision sensors. One can notice the camera glides along the control systems, where discharge parameters are inspected to ensure they remain within safe limits. In parallel with the embankment, spillway structures and vertical shafts are carved deep into the rock mass. Vertical excavation for these shafts involves the removal of thousands of tons of stone to create water conveyance paths. Reinforcement is installed within the shafts before concrete is placed in segmented stages. This allows for the control of hydraulic pressure during both the construction phase and the future operational phase of the dam. It is visible how the tunnel structures take shape once the excavation is complete. Workers install steel reinforcement and complex formwork before pouring the tunnel lining concrete in sections. This creates a waterproof, load-bearing shell for the discharge routes that must withstand immense pressure. The tunnel invert and the floors of the discharge structures are the next priority for the engineering teams. These floors provide the stable foundation upon which the entire water management system rests. Before the concrete is poured, reinforcement cages and specialized drainage layers are laid down in a specific sequence. The concrete is then delivered and poured in segments, with engineers maintaining strict control over the thickness and the final surface quality of the floor. It looks superficially simple to pour a flat surface, but in reality, the strength and smoothness of these sections determine the efficiency of the water flow. The material reaches its final structural density, completing the foundation and discharge network for the facility. 2018 and 2019 were the specific years when the first two turbine units initiated the generation of electricity. Why was this early activation necessary before the dam reached its final height? At first glance, the site appeared to be a chaotic construction zone, but in reality, these years signaled a critical shift into an active operating power plant. This energy serves a dual purpose, as it simultaneously fuels the local domestic grid and provides a live platform for technicians to monitor every hydraulic system under genuine load. The process is only gaining momentum. Engineers rely on this early production phase to verify complex design parameters and operational stability while the rest of the structure rises. It is visible how the massive concrete sections of the dam body continue to grow toward the sky. According to the established engineering schedule, the primary structure is projected to reach its final design elevation around the year 2029. The equipment gradually transitions to a state of permanent readiness, but this is just the beginning. Reservoir impoundment will not occur rapidly as the filling of the basin is managed with extreme caution over a calculated multi-year period. One can notice how the water level rises in controlled increments to ensure the geological stability of the surrounding terrain. It is currently projected that the Rogun Reservoir will reach its absolute maximum water level around the year 2036. Everything only gets more complicated as the hydraulic pressure increases against the newly cured concrete. Therefore, the year 2036 marks the ultimate milestone when the dam fully assumes its intended role in water regulation and maximum power generation. The camera glides along the vast expanse of the rising water, which will eventually drive all turbine units at their peak capacity. The material and the structure thus reach their final functional state, ready to operate for decades to come. From here, the project moves into its final phase of long-term energy stabilization. $6.3 billion is the estimated total construction cost required to bring the Rogun Dam to completion. Why would a nation commit such an immense sum to a single infrastructure project? It would seem more logical to distribute funds across multiple smaller sectors. But for Tajikistan, this dam is not a simple engineering endeavor. It is a national-scale financial gamble. This massive investment represents an amount equivalent to nearly 50% of the entire country's annual gross domestic product. For a small economy characterized by limited internal revenue and a heavy reliance on financial remittances from citizens working abroad, such a commitment creates an unprecedented level of financial strain. Rogun suffered from severe funding shortages for many consecutive years as the project stalled. International donors remained extremely cautious about providing capital, and this hesitation was not based solely on the immense physical scale or the technical complexity of the dam. The process is only gaining momentum. Political risks surrounding the project played an equally critical role in deterring foreign investment, as the dam sits at the center of a complex regional web. One can notice how the strategic positioning of the dam on the Vakhsh River creates a ripple effect across the borders of Central Asia. Downstream countries, particularly Uzbekistan, formed the core of these diplomatic and economic concerns. Because the Uzbek agricultural sector depends heavily on a consistent flow of water from the Amu Darya river system, the prospect of Tajikistan controlling a massive upstream reservoir raised long-term water security fears. At first glance, the project seemed stalled by these regional disputes, but in reality, it forced a shift in international oversight. In this difficult context, the World Bank agreed to become involved in the project's development only after making several firm demands. They required a series of completely independent feasibility studies, along with comprehensive regional impact assessments to ensure the dam would not destabilize the surrounding environment or economy. It gets more complex further on. These studies were intended to provide a technical foundation for a project that had previously been viewed through a purely political lens. If Rogun represents a survival gamble for a small and resource-poor nation in Central Asia, then the Three Gorges Dam stands as a different kind of monument. It serves as a physical demonstration of how a single dam can fundamentally reshape the economy and the entire energy order of a global superpower. The transformation of a river's power into industrial stability moves to the next phase of the narrative. 60 stories tall is the height of the massive concrete structure that forms the Three Gorges Dam, the strategic backbone of a complex hydropower ecosystem along the Yangtze Valley. Why was such a colossal barrier constructed despite the immense engineering difficulties involved? One could notice that the reservoir is so vast that its presence has permanently reshaped the geography and environmental landscape of the entire Three Gorges region. But without this controlled containment, the river would remain an unmanageable force of nature. This megadam demonstrates its capacity during full operation by eliminating up to 100 million tons of carbon emissions every single year. The process of regulating the river is only gaining momentum. Automated monitoring systems and massive sluice gates regulate the water flow for a territory that serves as the home for more than 400 million people. It seems simple to manage a river, but in reality, the impact of this structure reaches far beyond what raw numerical data can fully convey. Its greatest influence on the region is also its quietest and most consistent function, which is comprehensive flood control. One can notice how the water level remains stable even during heavy seasonal rains. And this is not the limit of its defensive capabilities. Before the dam existed, the Yangtze Basin suffered from the repeated devastation of multiple historic floods. In the year 1931, catastrophic flooding killed more than 145,000 people directly through the force of the water. Decades later, during the floods of 1954, the death toll surpassed 30,000 individuals. By the time the waters rose in 1998, the raging river swept away thousands of villages and took over 3,000 lives. The camera glides along the reinforced concrete walls that now prevent these tragedies, which previously caused China tens of billions of dollars in economic losses. It only looks obvious to build a wall against the water, but taming one of Asia's most unpredictable and destructive rivers required unparalleled industrial power. These historical figures and the scale of the damage explain why China felt compelled to establish a water shield of this magnitude. The equipment gradually manages the pressure of the current, ensuring the safety of millions downstream. From here, the management of the Yangtze moves into a phase of permanent stability and predictable energy production. 1994 marks the exact year the construction journey of the Three Gorges Dam truly began, as engineers initiated the preparation of a foundation capable of supporting a concrete structure 2,025 meters long and 181 meters tall. Why was such a massive scale necessary for the base, which reaches nearly 115 meters in thickness? A structure of this magnitude must withstand the relentless pressure of billions of tons of water pushing against its surface every single day. The process of securing this footing required tens of thousands of workers to remove an enormous volume of earth and rock, carving out deep foundation pits that descend to bedrock layers of granite hundreds of millions of years old. Each foundation pit functioned like a detailed geological cross-section, exposing the ancient backbone of the Three Gorges Valley. Only solid and unfractured bedrock could support a megadam of this unprecedented scale. At first glance, the rock appeared ready, but in reality, a massive network of grout holes stretching thousands of meters had to be drilled and injected with pressurized cement slurry. This process bonded the entire rock foundation into a single unified block and sealed even the tiniest cracks so that water could not seep through the subterranean layers. One can notice how every section of the foundation was monitored with geotechnical sensors to ensure no hidden weak points existed. The process is only gaining momentum. It is this mountain-solid foundation that became the permanent footing for the entire megastructure, allowing the Three Gorges Dam to stand firm against the powerful surging force of the Yangtze River for decades. Once the bedrock had been transformed into a stable foundation, the concrete pouring phase unfolded like a constant river of materials flowing through the vast construction site. Overhead, the steel arms of 20 tower cranes constantly swung back and forth, lifting and lowering batch after batch of concrete into more than 230 pouring blocks stretching along the former riverbed. On the ground, mixer trucks and pumping systems worked in perfect rhythm, delivering the heavy gray mixture to its precise locations as if the entire site were breathing to a single heartbeat. Every layer of concrete had to meet strict standards for thickness, moisture, and curing speed. It seems simple to pour liquid stone, but in reality, even the slightest deviation could create catastrophic weak points in the entire structure. Inside each block, a cooling pipe system reached deep into the core to keep internal temperatures stable and prevent expansion-related cracking during the chemical curing process. Surrounding these blocks, geotechnical sensors captured even the smallest movements, recording subtle signals invisible to the eye but critical to the safety of the dam. Day after day, new layers of concrete were poured over the previous ones, tier by tier, until the total volume placed surpassed 28 million cubic meters. This formed an enormous rock-solid mass ready for the next stages of the Three Gorges megaproject. But this is just the beginning. Before the project could move on to construction at higher elevations, engineers had to solve the most critical challenge: how to relocate the entire Yangtze River into a temporary passage while still handling its massive flow. To do this, a system of diversion tunnels was built as a strategic phase of the project, consisting of 3 tunnels carved deep into the mountainside. Each tunnel stretched more than 900 meters in length and stood 18 meters high, which is large enough to let the river pass through at speeds of up to 11,000 cubic meters per second. During this phase of construction, over 1,200,000 cubic meters of earth and rock were removed using drilling and mechanical cutting. One can notice how engineers avoided heavy blasting to prevent any vibrations that could affect the integrity of the bedrock foundation. Transition to the next level. Once the river was fully diverted into these tunnels, the original riverbed instantly became a dry work surface, protected by coffered dams and high-capacity pumping stations that kept conditions stable regardless of rain or flood season. As if a massive architectural form were slowly taking shape in the valley, the body of the Three Gorges Dam began to rise, layer by layer, with each new lift of concrete. Across a construction site spanning more than 100,000 square meters, steel scaffolding, hydraulic lifting platforms, and mobile gantry cranes formed a dense web of equipment. This allowed thousands of workers to operate at multiple elevations at the same time. This enormous structure was reinforced with more than 400,000 tons of steel, tied together across 28 dam segments running along the mountainside. The camera glides along the site where workers create a solid metal skeleton before each new layer of concrete is added. Each segment of the dam body was raised by 1 to 2 meters per cycle, forming giant steps pressed against the cliffs on both sides of the gorge. It only looks obvious to stack these blocks, but in reality, expansion joints were strategically placed to disperse stress, while shear resistant steel plates tightened each connection to ensure the entire dam operated as a unified structure. As it rose, the structure gradually tapered toward the crest, where the top width narrowed to just 40 meters, reaching the final designed height of 185 meters. This was the critical milestone needed to create a reservoir holding nearly 39 billion cubic meters of water behind it. The material is ready to move to the next processing phase without haste. 335 meters of elevation represent more than just a world record for the Rogun Dam project. Why does a single construction site carry the weight of an entire nation's survival on its concrete shoulders? It seems simple to view this as a standard hydroelectric power station, but in reality, it is a high-stakes stress test for Tajikistan's engineering capacity, financial reserves, and political stability. If the turbines eventually spin at full capacity, the nation will transform into the primary energy hub of Central Asia, but failure would leave behind the most expensive ruins in modern infrastructure history. Construction proceeds amidst a global environment of rapidly accelerating climate change. This shifts the focus from simple height to the complex interplay of regional interests. One can notice how the Vakhsh River is being harnessed within a framework of massive concrete and rock barriers. Everything only gets more complicated as the project enters its next phase. Upstream glaciers are retreating at a measurable pace, reducing the long-term predictability of water inflow. Simultaneously, downstream pressures from neighboring countries regarding irrigation rights and water sharing are mounting. The engineers must navigate these environmental constraints while the government manages the constant friction between capital requirements and strict timelines. The project operates at the intersection where infrastructure meets geopolitics. It does not end at this stage. It is visible how the massive dam wall gradually rises to its final height, fueled by millions of tons of material. Trust remains the most volatile resource in this equation, as investors and regional partners watch the progress of the world's tallest embankment. The future of the region is being shaped by the precise placement of rock and the controlled flow of water through deep diversion tunnels. Transition to the next level of energy production requires every calculation to hold true against both physical and political pressure. One can notice the heavy machinery moving across the crest of the dam with methodical precision. The process is only gaining momentum as the international community observes this monumental effort to secure energy independence. Thus, the steel and concrete reach the standards necessary to redefine the economic landscape of the entire territory. From here, the project moves toward its ultimate completion, carrying the expectations of millions into a new era of industrial development.